my pleasure now to introduce our next speaker, Professor Olivier Allix. He is well known to this audience. He also doesn't need much of introduction. He's Professor LMD Cachin. Among his numerous activities in the international community, I would like to mention that he is the president of the European Association on Computational Solid Mechanics, and he is known to all of us for his work on computational composite mechanics and multiscale models in nonlinear structural mechanics. Olivier, I don't want to take your time off. Please start.
Thank you very much, Gunther, for those kind words. Thanks to the organizer of the conference. It's a privilege and honor, and a little bit a challenge to talk after Michael, I must say. So in fact, with Michael, we split a little bit the type of research. He's doing, new and difficult research, so I go to an old and simple subject, but I hope to convince you that simple can be useful. Okay, so this is, so the motivation of what I call non-intrusive coupling strategies comes from my experience working with industries. So industrial partners ask often for us to do code developments within their own softwares. And this limits a lot what is possible to do in computational mechanics for industry today. Not all industry, but let's say classical industry. Therefore, as we like to do research, we have a tendency to develop our own development outcomes. But those developments, even if very interesting, are often academics. We cannot take into account the complexity of real industrial problems and so on. And so they do not benefit as they could to industry. Okay, so the non-intrusive paradigm aims at, in fact, combining the two worlds, aims at doing what we want to do within an industrial models. Okay? So the goal is, so it's very simple. Huh? So the goal is to able where you need to substitute a model a broad model of a part of an industrial parts with the model you think is much better and with the technique you think is much better to solve this model. Okay, so the idea is to couple a general model with all the technical complexity with, where needed, with a local model you think it's much better than the other one, with the computational technique that you like, and so on. And the tool, basically, today is quite easy. It's thanks to Python script. The price to pay in the method is iterative. So, in fact, it is as I said, it is an old subject. It comes from what in the past was called local global strategies. So there are a bunch of works which has been interesting in that areas. But in fact, what we try to do here is to do global local strategies in an extended way and in a non-intrusive way. So, in fact, this is something which start to gain interest in the research. The vocabulary comes from stochastic approaches, because to put a stochastic model within a classical code is difficult. So people have tried to do stochastic computation outside of the code. Okay, so that is why I use this vocabulary. And you have, within those methods, you have local global approaches from Whitecomb, the first, I think, which is weakly intrusive. You have the same goal is Harlequin framework, but it's strongly intrusive. And today, what I call the method is substitution. You substitute a part of something with another part. Okay, and there are works going on in a variety of domains. I will mention that what I try to do is what I call substitution, that there are very interesting work done by Duarte and other people in fluids and in solids by non-intrusive version of partition of unity methods. Okay, just to see what you can do, it's a very nice work from Passieux in Toulouse. In fact, he has an industrial code where XFM was not implemented, but the guy wanted to test XFM. So they had an XFM solvers. So like this, you can couple, you can substitute this part with this part. And really, what I call non-intrusive is that this thing has been done in an industrial software, and we never touch it. We don't touch a model, we don't touch a mesh, we don't touch anything. We want to replace this by this, doing natural computation on the industrial model. Okay, That is the goal. So another type of work today for people who are doing stochastics, in fact, usually you have uncertainty locally, so you can use your favorite global model and change, and so you substitute locally and you solve locally the stochastic problem. This is the work done, for example, at Nantes by Nui and others. So, but just to give a flavor of the method, it's very simple. It is an interface problem. So let's take this simple example here. This is my reference model. It can be nonlinear. You have holes. You can have detail. It is a sketch. Okay. And this is my initial model. It is a linear one, for example. And I have you a crude description of the local zone, both on model and on topology. Okay. So what I want to use is only two models. This model and this model, because this is the local one, and if I want, I can use an iterative solver. I can use what I want to solve this problem. Okay. So the question, how I compute the reference problem thanks to those two problems. In fact, so this one I will call it exact. This one I will call it global. This one I will call it fine. And for technical reason, I will need what I call approximate. That is this area, this model, the crude model of the local zone. Okay, so it's a very simple problem. In fact, we see that in order to get the correct solution, we should find additional interface forces to compensate from the differences between the crude approximation of the local model and the correct one. So abstractly, we have to find these forces which takes into account the differences of the two models, and will give the same displacement at the interface that the reference model and the same reaction forces. So very, very simple model. So just to say a little bit, because the algorithm is quite trivial, but let's say that to show the problem, we define the kind of nonlinear abstract operator, what is called the Schur complement, nonlinear Schur complement, where in fact, theoretically, the unknown is only the displacement and the interfaces, and here you have the data coming from the condensation of the forces. And here, in the model, in fact, we can have several cases. We can have the fine model, the approximate model of the zone of interest, the complementary part, which will be this model without this one, the exact one, and the global one. In non-intrusive technique, you can play only with fine model, approximate model, and global one. So the blue one, you never have it. Okay. But let's see how this can proceed. Just to give a word, what is this operator? In fact, in the classical linear sense, it is only the condensation of the problem on the interface. Okay, so it's very classical. So you do a classical condensation. Here we do not do that, of course, because the operators are nonlinear. But it is a classical. So from condensation, we know, for example, this is very important, that the exact Schur complement is the sum of the fine plus the complementary part, and that the forces also, the condensed forces, can be seen as a contribution of the fine part and contribution of the complementary part. And this is general properties true even in nonlinear cases. Okay, so what is an iterative operator? I should say that today things for when you have instabilities are unclear. So in fact, I am looking for a force on the interface which would give rise with the global model to the right displacement. Okay. But I know that in abstract format, the right displacement is the solution of the exact problem. Okay? So if I replace this guy in this solution, I end up with this equation. P is the solution of this abstract problem. F of P is equal to 0. So in fact, in the algorithm, we'll do a fixed point algorithm. So in fact, P solution of f de P equals 0 means that P is a fixed point of these operators. What is these operators? These operators is identity minus the Shor complement of the exact problem and the inverse Shor complement of the global one. What is these operators? Due to the properties that I say, it is the differences between the global and the exact, which mean the differences between the approximate modeling of the local zone with the exact one. Okay. And due to a property of a classical property of contractive operators, if you have this operator, which is larger in the sense of operator to this one, you converge. Otherwise, you compensate by a relaxation to ensure convergence. So convergence is really not difficult to prove when convergence exists. So, but now what is the corresponding algorithm? So we have a fixed points, Pn plus 1 equal identity minus Fpn, which when Pn plus 1 equal Pn minus this. But what is this guy? This guy is the displacement given by the solution of the global problem to Pn. So we do not inverse, we solve once. Okay. So we solve the global problem, then we replace this guy by the displacement. Here we have this guy. Due to the additive properties of the Shor complement, we can divide it in a fine contribution and a complementary part. Complementary part is not available in non-intrusive techniques, so we take the complementary of the complementary, which is approximate model, and we see that the forces that we have is the differences between the reaction forces of the complement exact of the approximate model of the complementary zone and the fine one. Okay, so very simple iterative algorithm. We compute the global model, we compute the reaction forces, we add this as a new force, and so on, and it converges. Okay, so now some developments. Of course, we can improve the rate of convergence, but the principle is here. So some developments. We have tried to use this scheme. I should give maybe something to solve that type of problem. I will come back to it. So in fact, it is just a scheme. You know, in industry usually deal with plate and shell models. But then you have local parts like joints, multiple joints, and so on. And in fact, the joint model in plate model are very crude. So we would like locally to be able to introduce a 3D model of the joint with all the non-linear complexity. Okay, I will come back to it now. So the idea it is of what we have done is to do the same thing in 2D that we do in 3D. That is, we start from a 2D computation. We associate a 3D solution from the plate solution. We'll see how we do that. So we will try to make match only 3D solution, the 3D solution associated to the plate solution with the 3D one of the bolt. Okay. So, in fact, we start for the plate solution, we have displacement forces, we go from here to the 3D solution, we get the displacement, and we compute now the extraction of the 2D forces, and we compute the residual in the 2D sense. So how do we compute this numerical lifting of the 2D solution? In fact, we use a kind of homogenization scheme. That is, we solve a small problem for a composite part, for example. We suppose that the plate works in the linear manner. So we decompose the problem in 5 basic problems for the Reissner-Medellin plates. And due to those 5 basic problems, we compute the stresses and displacement. And then we recover, associated for any type of plate loading, we recover the distribution of displacement and the distribution of forces through the thickness, thanks to 5 simple problems. These are pre-computed, and we use them after to lift the 2D solution and to couple the 2D solution to the 3D in the 3D sense. Okay, so how it is done? We say that our displacement in 3D will be the plate 1 plus this warping term multiplied by the corresponding force in the plate solution. This gives us the distribution of the displacement in 3D associated to the plate 1. Then, when we have done that, we send it to the local model. We compute the residual force, like before, which is the difference on the 3D one, of the 2D one, sorry, plus the condensation of the 3D reaction forces in the plate sense. This gives us our new forces, and so on. So here, what is the interest? So I start with a plate solution. Here I have a very crude model of the junction. And no, but the junction is quite complex. You have a screw, it is bolted, you have friction everywhere. So here you would like to use your favorite software. So in Cachan we have developed a software specialized for that type of things. That is a screw, taking into account the press stress in the screw, all the surfaces and so on. Okay. So I will compute this problem thanks to this problem which is done in industrial code and this one. Okay. So here what is interesting to see what happens. How does the fine model of the screw play a role? Here you see this is the plate solution associated the initial one and the correction in the linear regime. So you see very few correction at the beginning. But then, as soon as you become nonlinear in the screw, here there is an unscrewing of the bolt. You see that there are big differences, even in the global solution, between the plate solution outside of the screw and the one. Okay. So also with this method, it is interesting because you can, if you stop at the first iteration, in a way, it is what people do in industry, which is what they call submodeling approach. So we can also check the submodeling approach. For example, the first here, it is the sliding at this point B here, between the plate, and the sliding within the screw at point A. Here you see that for the first descent, here we get quite a correct value of the sliding far from the screw, but a very wrong one close to the screw. Okay, so it depends on what phenomena you want to look. So submodeling is not good if you go, let's say, far in sliding within the screw. And here, this is a full 3D computation. This is the solution obtained for the things. Here, you see that this is a full 3D solution. We were able to perform it. This is a converged solution. This is a non-converged solution. You see that within the screw, that is a submodeling approach. Within the screw, the submodeling approach is fully wrong. And you can see also, here it's more difficult, that in fact the sliding, the unscrewing of the bolt is not predicted with a submodeling approach. So the time of analysis, those problems are complex. You have unscrewing, you have things and so on. So if I take the fixed point is 2 hours and a half, let's say it's our reference, we can use acceleration techniques. And the best one is Allix. It's very simple, it's non-intrusive, and it works very well. And so in fact, for all this method, if we do the same thing, computing the screw with Aster, it is 6 times. So why? Because we develop a special software which is more for the computation of the joint, which is much more efficient than classical software. So now what we are dealing with? We're dealing with not one bolt, because it's not interesting, but a series of bolts. And in fact, in that case, the non-intrusive technique can be seen as a preconditioner. The plate solution can be seen as the preconditioner of the 3D ones. And then what is the interest? That for this bolt and this bolt, I can use always the same software, which has been developed only for one bolt, and to use it in parallel due to these techniques. So at the moment, we are computing hundreds of bolts with the same software in parallel, using the plate solution in that case as a preconditioner. Okay? So just to see that not everything is that simple, I'm working at the moment with Safran. Oh, sorry, I should have recognized my co-author, but I was so impressed by the talk of my course that I was perturbed. Sorry. So now we are dealing with this kind of thing, that is really complex constitutive law and non-linearity. And so things are not that simple. In fact, what people want to do, it is with Safran, they want really to be able to compute their structure with all the details, because they are at the limit. And today, without the details, the part that they are computing, in fact, without the details that they want to take into account is 4 months. Okay, what is this type of problem? We have, for example, combustion centers. We have a complex constitutive behaviors. It is viscoplastic behaviors. You have temperature and so on. And the goal is to compute, not for this part, but for another part I will show later. The goal is to compute the stabilized cycling associated to multiple flights. So you have very complex set of loadings. Okay. And today, to do that for a part, it takes them 4 months, but without introducing structural details. Okay. So when we have tried our methods, in that case, I will show the example, we have had a lot of problems. Simple one, sorry. Because in fact, you see, the global model is nonlinear, viscoplastic. The local model is nonlinear. And the detailed local model, you have holes, you have details. And so you use Abacus. We use Abacus. And in Abacus, to converge, you put cutbacks. So you don't know it. You give a certain time. And Abacus will do several cutbacks in order to converge. But in fact, in the different models, the cutbacks are not the same. So at the end, the non-intrusive method that I presented, you converge, but you do not converge to the correct solution, to the reference solution. For example, here we had on the maximum stress an error of 20 megapascal, and the goal of the industrial would be not more than 1 megapascal of error. Okay. So what we do, in fact, oh, sorry. Yes. So, I'm sorry. Oop, what happens? One step before. Yes. Okay. So what we do, in fact, is that we start with a global model. The global model in Abacus, you have to look at the cutback. For example, let's say I want to go to this step on the global model in this step. Abacus will divide, depending on the problem of convergence of the local model, will divide the step in those steps. Okay. Then we have to recompute the global model taking into these steps into account in order then to make the non-intrusive approach locally between the time step imposed by Abacus. And what is nice is that we can solve the local problem. We have to match this time step. We can solve the local problem if needed, and introducing other cutbacks, but then the method converges. It is a practical problem. So just an example. This is a global problem. Here you will see that there could be a lot of it. So people want to introduce holes in order to cool down the process. So we have an auxiliary model. We want to see if we introduce the holes in this part, what happens. Okay, so here the model now is something like, oh, it's boring, sorry. The global model is 1 million degrees of freedom. The auxiliary one is this number of freedom. It is fully viscoplastic and so on. And so, with the method now, with the method of cutback, we are able to predict precisely what is the distribution of the plastic strain around the hole due to the local detail with a precision of less of 1%. So that is, now the method works in an industrial context, let's say. How much do I have time? 5 minutes. So, I just want to say that now I'm working with Umberto Perego to extend the method in dynamics, in explicit dynamics. So, I have no time to give detail in order to keep question, but let's say that this has been done, and that today the method has been introduced in Abacus Explicit. So, what is nice that is you are able to use this type of model. You have a plate model, you have a 3D model to take into account delamination. So the plate model, you have it is in explicit. So you have a time step of the critical time step of the plate model. Okay. Then you have a local model with delamination, very fine 3D. Then you have another time step, and the things are coupled, and you converge to a reference solution, which is in your plate within in dynamic explicit, the model of the plate plus the model of the local model of your composite plates, and you are able to compute it in a, we would say, multi-scale space and time manner. Okay. So this is a comparison with the reference model. This is a substitution. Reference, this is a reference model. You see here the extension of delamination. Extension of delamination. Extension of delamination. Here it is not the reference model, it is what they used previously. It is a tie model. So they tie the local model with the 3D one, and you see that you have a lot of spurious delamination. We have a little bit in our model, but less, and the method is non-intrusive. So I will try to conclude. Sorry, I've been maybe a little bit long. So I think that non-intrusive computational approach have broad capability to easily couple softwares. I think my initial interest was to use the software I was developing for composites and to use them within an industrial context, which was not possible. But in fact, today the demand of industrial, it is amazing, is to be able to do reanalysis of their own problem. Because, in fact, it's so complex to make meshes. For some meshes, they are at the limit. So if they go to higher number of degrees of freedom, they are not able to compute the problem, and so on and so on. So there is a lot of problem in industry where they are keen to use this type of method, and they ask us to develop the method in sometimes quite a crazy way. So we try to answer to the problem. So in fact, this allows to perform exact reanalysis in model and meshes. And so the current issue I'm working on with some colleague is you see that there is a question of precision, especially in viscoplasticity, high cyclic fatigue is a very important one. So we have started to work on guaranteed local error bounds in non-intrusive approaches with Pedro Diez. For the moment, it's a linear setting. Of course, if we want to deal with a very large number of cycles, we have to imagine a multi-scale approach in time for a large number of cycles. So this is the current work. We work, as I said, in a way to use those non-intrusive approaches to introduce parallel computing in industrial softwares. I think it's a very simple and nice way to introduce parallel computing in industrial software. We are extending the explicit coupling to explicit implicit. And something which is quite open, to my opinion, at least on the theoretical point of view, is extension to instability. Okay, thank you very much.